Now that I've defined cosets of rings, let's define a quotient ring. Let's consider the set of all cosets of J where J is some ideal. We're going to denote this by A divided by J, or A mod J. This consists of all the elements J plus A, J plus B, J plus C, etc., where this A, B, and C belongs to my ring A. And this is going to be my quotient ring, similarly to how whenever we were talking about groups, it was a quotient group. And in the previous video, I proved that the operations for coset addition and multiplication were well defined. So the set A mod J with coset addition and multiplication is a ring. And coset addition and multiplication are associative, and multiplication is distributed over addition. These are facts that can be very routinely checked, and I'll leave them to you to check them. Instead, I want to look at the zero element and the negatives. The zero element is defined as just the ideal J, or J plus 0. This is because if we have J plus A, where A is any element, so we have any coset, plus J plus 0, this is defined as J plus A plus 0, which is J plus A, which is exactly what we need for a zero element. For negative, if I start with the set J plus A, its negative is going to be J plus negative A. If I then add these, we have J plus A plus J plus minus A. Under our operation, this is J plus A plus minus A. And we know A plus minus A is 0, and J plus 0 is just J. So when I add these two elements, I get back to my zero element, so this would be the negative. And so this is known as the quotient ring. The next big result that follows what we did for quotient groups is that A mod J is a homomorphic image of A. And this is done by the function f of x equal to j plus x. And so we need to check that this is an onto homomorphism. And I'm not going to prove that directly. It follows very, very similarly to how we prove this for groups. So I encourage you to try to look through it. So let's look at some examples of these quotient rings. Let's start by looking at the quotient ring Z mod the subgroup generated by 4. So Z plus 0. Let's start with the subgroup generated by 4 plus 0. In the integers, the subgroup generated by 4 looks like -8, -4, 0, 4, 8, etc. We also have the subgroup generated by 4 plus 1. This would be -7, -3, 1, 5, 9. We can add 2. This gets us -6, -2, 2, 6, 10, etc. Adding 3 gives us -5, -1, 3, 7, 11. And we can double check that if we add 4, we get back up here to this coset of the subgroup generated by 4 plus 0. And you can check, but these will be the only 4. Let's refer to these as 0 bar, 1 bar, 2 bar, and 3 bar. And you can double check, but this is going to be the additive and multiplicative table for these cosets. And so we can see that this looks very similar to Z4, the ring Z4. And so a lot of times we'll refer to this, the integers mod the subgroup generated by 4, as the ring Z4. Similarly to how we define this modular arithmetic of groups. For my next one, let's look at Z6 mod the subgroup generated by 3. So we start by adding 0. That'll just get us my original subgroup, 0 and 3. If we add 1, we get 1, 4. adding 2 would get us 2, 5. Adding 3 gets us back to 0, 3. Adding 4 gets us to 1, 4. And adding 5 gets us to 2, 5. So these are my 3 sets here. Let's refer to them as 0 bar, 1 bar, and 2 bar. To fill in our additive table, the 0 bar works just like the additive identity. For 1 plus 1, what I'm really looking at is this subgroup generated by 3 plus 1 plus the subgroup generated by 3 plus 1. We define this to be the subgroup generated by 3 plus 1 plus 1. That's the subgroup generated by 3 plus 2, which is the same thing as 2 bar. To do 1 bar plus 2 bar, that would be the subgroup generated by 3 plus 1, plus the subgroup generated by 3 plus 2. This is defined as the subgroup generated by 3 plus 1 plus 2. We know that 1 plus 2 is 3, so the subgroup generated by 3 plus 3, which is the same thing as 0 bar. And similarly, we can fill in the rest of this additive table. Now let's look at the multiplicative table. Since 0 is my additive identity, anything times 0 is going to be 0. Let's look at 1 bar times 1 bar. This is the subgroup generated by 3 plus 1 times the subgroup generated by 3 plus 1. We define this as the subgroup generated by 3 plus 1 times 1, which is the subgroup generated by 3 plus 1, or 1 bar. Similarly, for this spot, we would get 2 bar. And for 2 bar, 1 bar, we would get 2 bar. For my last entry, we would have the subgroup generated by 3 plus 2 times the subgroup generated by 3 plus 2. This is defined as the subgroup generated by 3 plus 2 times 2. 2 times 2 is 4, and the subgroup generated by 3 plus 4 is the same thing as 1 bar. So here's my table for this particular quotient ring. Once again, similarly to quotient groups, we have that if F goes from A to B, is a homomorphism from a ring A onto a ring B, and K is the kernel of F, then B is isomorphic to A mod K. And I did prove this for groups, and it's going to follow very, very similarly for rings, so I'm not going to prove it directly. But let's look at an example of using this. Earlier in this video, I looked at Z6 mod the subgroup generated by 3, and I had 3 elements, which I called 0 bar, 1 bar, and 2 bar. And you may have noticed it looked very, very similar to just Z3. So let's prove that these are actually the same. So I need a function going from Z6 to Z3, and it needs to be onto. So Z6 consists of 0, 1, 2, 3, 4, 5. And Z3 consists of 0, 1, 2, and we're going to map those elements directly. I'm going to map 3 to 0, 4 to 1, and 5 to 2. And you can double check that this is a homomorphism, and we can see that the kernel of this consists of the elements 0 and 3, which is just the subgroup generated by 3. So by my theorem, we have that Z3 is isomorphic to Z6 mod the subgroup generated by 3.